I'm going to talk about sums and differences of rational expressions. And if you recall, when I was talking about products and quotients, we basically did it the same way that we handled numerical fractions. The variables didn't get special treatment. Okay, same thing is going to hold true for sums and differences. We're going to do the same thing we do with numerical fractions. The variables, again, aren't going to get special treatment. So, for example, let's say that I had 5 over x plus 3 over x. Well, we know we are allowed to add fractions when the denominators are the same. Okay? That doesn't change just because the denominator is a variable. So here we would get 8 over x. All right? It holds true even if we have something a little bit more complicated like 8 over y squared plus 10 over y squared. Okay, once again, the denominators are the same, so that's all we need to get the green light to add the numerators. 18 over y squared. All right, let's do a difference now. So how about 18 over m squared minus 5 over m squared? Numerators are denominators are the same, so we can subtract the numerators. 18 minus 5 is 13. Okay? And the same idea applies again as the denominator slowly gets more complicated. Let's say I had 8y divided by y minus 1 plus minus 3y over y minus 1. Okay, so again, denominators are the same, so we're good to go. 8 apples minus 3 apples is 5 apples. That's my attempt at trying to clearly explain how I added the numerators together to get 5y. So we get that. All right. So now, what if the denominators are not the same? Well, then we have to make them the same. Otherwise, we're not going to be able to combine the fractions. Okay? So let's do an example of that. Suppose we had 4z over z minus 3, and we wanted to add that to z over 3 minus z. Okay, you may recall a couple times I've said that when you switch the order in a binomial, it's like multiplying by minus 1. Okay, so let's take advantage of that. Let's keep the first rational expression the same. Let's multiply the second expression. Let's multiply the top by negative 1. So that turns the z into a minus z. Let's multiply the bottom by minus 1, which is equivalent to just flipping the order. Okay, now we have this. Well, okay, now the denominators are the same, so we're good to go. Okay. Now, as before, as I showed you in this example, we could keep tweaking it in different ways as necessary to get the denominators the same. What about if we had this? What if we had 15 over 4x squared, and we wanted to add that to 25 over 18x? So, first of all, let's get the least common denominator, which is exactly what we would do if we had numbers. Okay, here we're still going to have the least common denominator, but it's going to involve variables. So the least common denominator of 4 and 18 is 36. The least common denominator of x squared and x is x squared. So what I want to do is I want to make both fractions, I want to convert both fractions to an equivalent version that has a denominator of 36x squared. Okay? Now, what do I have to do to the first denominator to turn it into that? Well, I have to multiply it by 4, right? That means I have to multiply the numerator by 4. Okay? What about the second fraction? I had to multiply the denominator by 2x, so I have to multiply the numerator by 2x. Okay? Now, as you can see, that was all worth it because now we can really combine the fractions. So the bottom stays the same. The top, let's see, 4 times 15 is 60 plus 50x. Okay, and that's as far as we could go. Okay? Let's now finish by doing what might look like a crazy one. Okay? But it uses all the same ideas we've already talked about. 5 times x minus 4 divided by x squared minus 2x plus 1 minus 3x over x squared plus 4x minus 5. All right, step 1 is to factor. Okay, so let me factor the denominators of each. The numerators can't be factored in this case. X minus 1 times x minus 1. You can write it as x minus 1 squared if you like. The second denominator, x plus 5x minus 1. Okay, so the denominators are not the same. The least common denominator will be the first denominator multiplied by x plus 5. Okay? So the denominator I'm going to want both of them to have is x minus 1 squared times x plus 5. Okay, so in order to convert the first denominator to the desired denominator, I have to multiply by x plus 5, so let's multiply the numerator as well. For the second one, I had to multiply the denominator by x minus 1, so let's multiply the numerator by x minus 1. Okay, now let's combine this whole mess and let's see if we can simplify anything. So we're going to get a single fraction with a denominator of x minus 1 squared times x plus 5. And let me expand both numerators and do the subtraction. And let's see what we get. Okay, so I'll do it in a different color. So the first product of binomials expands to 5x squared plus 21x minus 20. The second binomial, 3x squared minus 3x, but when we subtract it, we get minus 3x squared plus 3x. Okay, notice that the 3x is positive. When you distribute the 3x, when you multiply that by minus 1, you get a minus 3x. However, you have another minus sitting on the outside ready to change things. Okay, so putting it all together, you get a plus 3x there. All right, so now let's see if we can do anything to that. 5x squared minus 3x squared, that gives 2x squared left over. 21x plus 3x gives 24x left over. And I think that's all we can do. So putting it all together, 2x squared plus 24x minus 20 multiplied by x minus 1 squared times x plus 5. Now you could try to factor the numerator and see if you get any of the factors end up canceling with something in the denominator. It won't, but you want to be open to that fact. But in this case, that's as much as we could simplify it. So that is the final answer.